Okay, hey everybody, welcome to a video on section 6.4. Let me acknowledge up front that this will not be my best work. I will receive no teaching awards for this, but I did want to get it out quickly as possible, so you could watch it as quickly as you wanted. In particular, maybe you could watch it before class time tomorrow, because I'll be in a Zoom link tomorrow at our class time when class time starts. So if you have questions, you can show up and ask. Anyway, so this is not an ideal setup. I want to use my laptop and my iPad. So the best way to do that, I think, is to do a Zoom meeting where I record myself talking to myself. So Zoom, inescapable, isn't it? Always on Zoom, no matter what, aren't we? So anyway, let's get to it, and I'll share my screen. Okay, so section 6.4, and I'll try to make this as brief as possible because I know this is not compelling viewing. But section 6.4 is a super nice section. And I wish we were doing it in person. I mean, obviously, with the extenuating circumstances, it's, I think, a good idea not to do it in person tomorrow. But I wish we could do it in person because this is a really nice section. As the point here suggests, we made it to what you would actually care about if you're going to study the Laplace transform. So you don't study it for its own sake, although I guess some people might. But for us anyway, we're studying it because it can handle initial value problems that arise from spring mass or circuit systems with pretty natural behavior in terms of external forces. It's just those external forces are not continuous. So when you have an external force that's not continuous, previous sections gave up immediately when they would see such problems. Previous sections just can't handle that kind of thing, but the Laplace transform can. Laplace transform is very powerful. So it can handle discontinuous forcing functions like it's nothing. It doesn't care. So I just want to show you that so that now we can finally see the point of the first three sections. So let's do a spring mass system problem. So we're not going to beat around the bush here, are we? So I'm just going to give you the coefficients. 2, damping is 1. And now here's what's new. We couldn't do this in chapter 3. At time 5, you switch on a motor and shoot 1 Newton of force into the system. You keep doing that till time 20 when you flip a switch and the force is off. There's no initial displacement or velocity. So this left-hand side should look very familiar to you. This right-hand side should look familiar to you from class last time. So this is the notation that captures this English. And the nice thing about this notation is we have a theorem that tells you how to transform that. Like, what's the Laplace transform of that? So that if you want to solve this using the Laplace transform, you can. So let's walk through that. So when you're going to solve an initial value problem using Laplace, the first thing you do is transform both sides. And so to do that, you have to know how to transform these step functions, which we do. The transform of u5 is e to the negative 5s over s. Transform of u20 is e to the negative 20s over s. So there you go. That's the s version of this t function. That's a function of t right there. This left-hand side is just like before. Twice u becomes twice L of u when you Laplace everything. U prime becomes S L of u minus u of 0. We've used that a couple of times now. That's the transform of a derivative. And then here's the transform of the second derivative, but with a 2 on it. Right, so if you take away the 2, you're just looking at that formula we've used several times. So once you transform the equation, that's step 1. Step 2 is to isolate L of u and put the initial values in there so you actually know what u of 0 and u prime of 0 are. In this problem, these initial values are as nice as they can be, so that this term all go away. So all you're left with is L of u terms with a 2s squared plus an s plus a 2. So isolating L of u, you just divide, you factor out the L of u and divide by that 2s squared plus s plus 2. And there you go. So I don't know what u of t is yet, but I know the s version of u of t. Like this is u right here, but in s language. So to get u of t itself, we have to go from s to t. And I've started the work here just to show you the parallel of what we did last time. So if you wanted to invert this thing here, right here, as we discussed last time, the way to do it is to peel the decaying exponentials off. You deal with just this thing right here. So you find the t version of that, and then this decaying exponential has two effects. Once you find the t version of this, you shove to the right by 5, and then you pick up a u5. And over here, you shove to the right by 20 and pick up a u20. That's what we talked about last time. So hopefully that's familiar to you and you know what I'm talking about. Okay, now the question is, how do you find the t version of this? Well, as we've discussed before, if the denominator factors, you can do a partial fractions decomposition and go to the table. And this denominator is factored. So you could ask Wolfram to break this into an over s piece and an over 2s squared plus s plus 2 piece. You could do that. The only issue is this 2s squared plus s plus 2 doesn't factor any further. And that's sort of a computational algebraic problem for us, because if you go to the table, okay, so there's this linear term here, this plus s. So if you go to the table and you look for entries where that linear term is down there, you're not going to get a sine or a cosine. What is happening? I don't want to strike through. It's going to make me do it anyway. All right. Well, whatever. You're not going to get a sine or a cosine because there's nothing linear down here, but oh, there's a strike through already. Look at these down here. I mean, this is factored, but there's a minus 2as right here and a minus 2as right there. So if you have a linear s term down below, you're going to use line 19 or line 20, but to use them, look at how you got s minus a squared. So the linear term has been subsumed into the squared piece. To do that requires completing the square. So in other words, to go from this 2s squared plus s plus 2 to something that looks like this requires completing the square. And I mean, that's not a big deal. All of you learned how to do that in Algebra 1. But at some point, we have to sort of draw a line and say, we're done doing algebraic manipulations because it takes too much time. So here, we're just not going to deal with this because we've sort of hit the wall where we're like, enough, you know, I'm not going to do any more algebra because I don't feel like completing the square. So I'm going to show you a shortcut here in a second, but let me just say as clearly as I can here, this problem is a fair exam problem without using any sort of shortcut if this denominator factored all the way. What if this became s plus 1, s plus 2, s plus 1 times s plus 2? So you would have 1 over s times s plus 1 times s plus 2. What if you could do that? Then partial fractions just breaks it into 3 pieces. And you just boom, boom, boom. Each of the 3 individually invert, and you're done. Just like we did last time in class. So you don't need the shortcut I'm about to show you if this thing factors all the way. So again, this problem without a shortcut, you could do, and I could ask you to do on an exam without doing what we're about to do. Now, okay, right here, this S stuff, as you might expect, Wolfram Alpha knows what the T version of this is. Wolfram Alpha, like it knows this table, and Wolfram Alpha, if it's good at anything, it's good at algebra, doing algebraic manipulations. So Wolfram Alpha could see this, and it also knows, right, that if you have a decaying exponential, what the effects are that you shove to the right by 5 and pick up a U5, it knows all that stuff. So we can leverage that to our advantage. Wolfram Alpha, where are you at? Here we go. So you can ask it to give you the T version of this. So I've pre-typed it, but the syntax is inverse Laplace transform, and you type in your S stuff. And when you hit enter, See, it says, oh, inverse of this S stuff, okay. And then it gives you the output. There you go. Now, several things to say about this. First of all, step functions don't have any universal notation. So our book says U sub C. Wolfram Alpha says theta of T minus something. So this theta of T minus 5, in our language, that's U5. Theta of T minus 20, that's U sub 20. So that's the first thing to note. And it says down here, theta is a Heaviside step function. So step function like we have. So that's the first thing to know. Wolfram uses different notation for the step functions. Okay. The next thing to point out is that, what a mess. Like, look at this. Isn't that a big old mess? And, you know, the answer is yes. So one reaction you might have is a negative reaction. Like, oh, what a mess. I don't like that. And I don't want to tell you how to feel, but that's the wrong reaction. It's wrong because what we're trying to model is a pretty complex process. So we were trying to model the movement of a mass on a spring where the movement kind of comes in three pieces. So notice initially nothing's going on. No displacement, no initial velocity, and this force hasn't come online yet. So until time 5, nothing's happening. But then at time 5, something happens. The system fires up, you fire in 1 Newton, that goes for 15 seconds, and then you turn it off. And then from time 20 on, it does something else. So that's a pretty complex thing to model. So it's actually kind of a miracle that you can write down an answer at all. And look, I mean, so it's actually really nice that you can write this down. And furthermore, if you just think about qualitatively, pictorially, graphically, what's happening in the system, Wolfram will show you that too. Look at this. This is a graph of this big old mess function up above. And notice just how natural this is. So like we said, for the first 5 seconds, nothing's going on. But then at time 5, look what happens. You flip that switch and you shoot 1 Newton into the system for a while. And that 1 Newton forces the mass away from equilibrium and the graph up. So the force forces the mass away from equilibrium, but there's damping in the system. So the damping and the force kind of fight with each other. And the damping kind of wins in the sense that the motion dies down. But the force kind of wins in that it keeps the mass away from equilibrium. So the force and the damping kind of fall into a truce with the movement dying down, but dying down away from equilibrium. But then notice what happens at time 20, you flip that switch and the force goes off. And so now, like, the mass goes back to where it wants to be at equilibrium, but flies past it due to momentum. And then around here, the only thing left in the system to affect the motion is damping. So like momentum kind of carries it for a little bit, and then damping kills the motion. So the thing is, this graph is perfectly natural, I think. Like, it does exactly what you think the mass is doing over time, given the physicality of the situation. But this graph, it's hard to write down a single function that has that graph, don't you think? But you can do it, is that. So if you want to write down a function where the graph comes in like 3 pieces and there's sine waves that are dying down or whatever, you pay a price for that. And this is the price you pay. Now, the next thing I want to point out is that if you kind of let your eyes go fuzzy and don't focus on the exact specifics of this function is also totally natural. It comes in 2 pieces. So the first piece is this top piece, and there's a U5 right there, a U5 times everything. So what that means is that this function here, this combination of sine and cosine and decaying exponential, that doesn't start up until time 5. So before time 5, nothing's going on. And then at time 5, this function comes online. And what's the deal with this function? Well, it's got sines and cosines, so it's wavy. But that's all multiplied by a decaying exponential. So the waviness will die down. But there's this free-floating constant right here, 15 over 30, so a half. So there's like this free floating half that doesn't see this decaying exponential. And that's why down here in the graph, see how it's like dying down around half? So if nothing else happened in the system, you would just, the mass would just stay at height half a meter away from equilibrium forever. But what happens next? Minus at time 20, this stuff comes online. You see that? And now you got like a 15/30 minus a 15/30. So there's some like cancellation effect from this other stuff. And this other stuff is like sine, cosine attached to a decaying exponential. So this other stuff dies down too, but like it, by turning this on, you force things back down to equilibrium and the motion dies down. So it's like this stuff here is from time 5 to 20, like keeping the motion going, but away from equilibrium. And then when you flip that switch off, this kicks in and sort of cancels it all out. And the motion eventually dies down to 0 at equilibrium. So that's super nice that you can get that. Okay, I want to show you one more example real quick. I've already droned on too long, but one last point to make here is, one last question you should have is, if Wolfram can do that for me, why do I ever bother like manipulating this by hand? Why don't I always just scurry off to Wolfram no matter what and get the inverse Laplace transform? And the answer is because I don't want everything to be a black box. Now, we can't do everything all the time. Like we can't do everything from first principles all the time and also use technology. We have to make choices about how we spend our time. But I think it would be bad if you knew nothing about what was happening here. And then Wolfram is just this complete mystery. Like you would have no idea what's happening. You'd have no idea what Wolfram's even outputting to you, maybe. So that's the reason why for some of the smaller problems, we do it without Wolfram doing everything for us, so we understand what's happening. And then when we get to something like this, we acknowledge that we understand what's happening. Like, oh, Wolfram's going to use that theorem where this thing causes a U5 to show up and a T-5 to show up in the T, and so on. Wolfram's going to complete the square for me, and so on. So anyway, but I don't want it to be a total mystery. Okay, so now I'm going to switch to my iPad real quick for one more example. And if we were in class, I would just have you do this. Okay. Let's see. Great. You are sharing your screen. Okay, that's good to know. And then I come over here. Let me point out real quick, I've written the answer on the handout in the friendliest way, just so you can see that theorem being used. See the T-5 there, T-5, T-5. Wolfram writes it a little differently, but it's of course equivalent. You can see that theorem from last time showing up in the answer as I wrote it. Now, and also, when you write your answers, use the notation from the book, U5, U20. Don't use Wolfram's notation. Okay. So here's one more example, just real quick, just to show you what you'll do in the homework. So it's the same setup as before, but there's some differences. No damping, external force is 3, initial velocity 0.5. So see if you agree with this. I claim this is now the initial volume or initial value problem we care about. On the left-hand side, there's no more damping, but the 2's stay. And then now instead of 1 Newton, we have 3 Newtons. No initial displacement, but we now do have an initial velocity like that. So there's the initial value problem now. So let me show you in this homework set what you would do. Okay, so we transform both sides. So I have, this doesn't change. The transform of U double prime. Twice U prime of 0, and then plus 2 L of U, and equals 3 e to the negative 5s. Okay. Make sure my 5's and my s's are distinct. 5s for s minus 3 e to the negative 20 over s. Okay, so now it's time to plug in my values. So 2s squared L of u. U of 0 is still 0, but u prime of 0 is a half. So I get minus, well, get minus 1 right there. This is minus 1 and plus 2 L of u. And that equals the same on the right-hand side. So now, if you let me do this all in one step, I have L of u times 2s squared plus 2 equals 3 e to the negative 5s over s plus 3 e to the negative 20s over s plus 1. And so finally, I get isolating like this. Divide everything by 2s squared plus 2. Okay. Now, I'm going to use Wolfram to invert this, but let me just point out, scratch work here. Something like this is fair game for an exam without using a Wolfram Laplace inverter, because this denominator is so much nicer. There's no linear term in that quadratic. So if I ask Wolfram to partial fractions that for me, let me just do that real quick. So I'm doing 1 over s and then 2 plus 2x squared. Just doing this on my laptop. I don't want to switch back and forth. Okay. Wolfram tells me this. Okay. 1/2 times 1 over s. And half s squared plus 1. Make this a little clearer. And the thing is, this and this are like immediately gettable from the table. So let me bring the table up again on my laptop. I'm not going to switch back and forth just to save time. But s over s squared plus 1, that's just a cosine of t, and 1 over s is just a 1. So you would do like this. u5 1/2 times 1 minus 1/2 cosine t minus 5. So all I'm saying is this is now much nicer. This is just partial fractions can tell you what to do here. So it would be fair game on an exam to just say, look, when you get to something like this, you can just do it. You don't need to have Wolfram do it for you. So it's not a black box. Okay. Or on an exam, I might just say you can use the inverse calculator. But again, for something like this, you would never have to do this by hand. But for something like this, it's a possibility just because we've already done this. Like this is something we've done multiple times. Okay, so anyway, let's get the answer and be done with it. Whoop. So here, if you ask Wolfram Alpha to invert that for you, then you get this answer right here. Again, Wolfram might not write it so nicely, and it's going to do, Wolfram's going to have a theta t minus 5. But that's what it will give you, this answer at the bottom. And so again, you could ask this answer, does this make sense? Like what's happening here? So let's ask ourselves, does this answer make sense? And notice there's this free floating sign right here. free floating sign. What's the deal with that? Well, in this problem, see the initial velocity, you smack the mass to get it moving before the force kicks in. So that force of 3 newtons, that's at time 5, but at time 0, you're already forcing the mass to move. So that's where that sign comes from. And notice there's no decaying exponential attached to it. So that sign's not dying down. It's going to wave forever. Why is that? Because there's no damping. And similarly, like these, why is there no decaying exponential? Because there's no damping. So when you turn that force on, it's just going to make the waves even bigger than they were before. And then they won't die down afterwards. So any like momentum you introduce into the system never dissipates. So anyway, here's the effect right here. This is the effect of turning on the force. And then of course, there's some effect of turning off the force, right? When you turn off that 3, you're not forcing it away from equilibrium anymore. So this here, I know I'm making this like overly marked up. This is the effect of forcing it away from equilibrium at 3 newtons for a while. So even though there's no damping, you're still forcing it away from equilibrium. So it's not like it's just going to wave at equilibrium. But then this here, this is like, oh, when I turn that switch off, it goes back to equilibrium, past equilibrium, right? So there's nothing to stop it because momentum carries it. And then it'll be symmetric about the x-axis or the t-axis after that. So that's what's happening there. And if you want to get a picture of a graph here, just ask Wolfram. Ask it to invert this for you, and it'll show you the t graph. Okay, so now just real quick, how do I stop sharing this? Like this? Okay. Real quick before I pass out, let's look at the homework. Okay, this is the bulk of the homework for this section. Your textbook has forgotten why it cares about the Laplace transform. So it doesn't ask you these spring mass questions for reasons that don't make any sense to me. I mean, the book is like, well, that was 3 chapters ago, so we forgot, but I didn't forget. Anyway, so it says here, so on all of these problems, no matter how simple the S function is, just use the Laplace inverse calculator. So again, with the understanding that sometimes you might not be able to do that. And all of next week, there's no new material. So all of next week, we're going to practice with the transform, practice with spring mass. And so by the time you take your exam, it should be crystal clear when you're allowed to use what, and hopefully how to do these problems is crystal clear. Okay, so this has gone on probably too long. So I will figure out how to stop recording now. And hopefully I'll see you on Friday.